Hi everyone, today we are going to have a look at the basics of logic gates. They are pretty useful things in terms of electronic circuits. They allow us to establish some different relationship between sets of inputs with sets of outputs. So things like if such and such conditions are satisfied, then a switch will turn on or turn off, and so on. Now, let's look at the basics of some logic gates. Now, these ones, you probably already know these. We have our NOT and OR gate, and then NAND and NOR gates. They're pretty straightforward. So, NOT gate, what it does, it inverts your input. So you have input low, the output will be high. If the input is high, then output will be low. Yeah. Well, in terms of electronic circuits, these lows and highs just means voltage. So if you apply voltage here, there will be nothing over there. If you have nothing here, there will be a voltage high here. And that's pretty much it. Most circuits you use, like basic electronic circuits, they're probably 5 volts. So if you apply 5 volts at this end, you get 0 here. If you apply 0 here, you get 5 here, and so on. AND gate. AND gate will have 2 inputs. Yeah. Now, AND gate basically tries to check if both conditions are met. So if both of them are low, then the input will be low. If either one of them is low, the input will still be low. And the output will still be low. The output only becomes high if both inputs are high. So that's AND, because A and B have to be high for the output to be high. Now, OR is slightly different. So OR, if neither the inputs are high, of course the output is low, but OR, so A or B, so if either one of the input is high, then output is also high. So 1, 0, so 1, yep. And then, of course, if both inputs are high, then the output will be high as well. Now, let's look at the other two, NAND and the NOR gates. Well, they basically do the opposite of AND. So if both inputs are low, AND will give us a low output, but NAND inverts it and turns into 1. Similarly, if only one of the input is high, the output will be low, but NAND inverts it again. So it's basically does exactly the opposite of AND. Similarly, NOR does the opposite of the OR gate. So if both inputs are low, then the outputs will be OR gate will be 0, but the NOR gate will invert that and give us a 1. Similarly, 0, 1, of course, it's OR gate, so one of them is on, so it should be on, but then inverts it and becomes 0, and 1, 0, 0, and of course, last one, if both are on, according to OR gate, it should be on, but it turns off and becomes 0. So these are the basic functions of some simple logic gates. Of course, do you understand that these are just abstract representations? Yep, they are just diagrams. What we are now going to have a look at is actual electronic constructions that make these work. So what kind of electronics are built into circuits to allow this kind of functionality? So basically, we look at the maps. Now we are going to look at the actual ground represented by the maps. And so before we go into that, let's have a look at basics of some electronics that actually go into them. The two main ones, that are important for logic gates are diodes and transistors. So just a quick review if you don't remember what they are now. Diodes, basically, it controls the direction of the current flow. So here we have a triangle pointing towards the right, which means the current can only go from left to right in our diagram. So that's pretty straightforward, while the current in the other direction is prohibited. Now, transistors, they are slightly more complicated. So what transistors do is they act as a switch. So we have a base, a collector, and an emitter. So what happens is if a small current goes into the base, then the transistor gets switched on, allowing a bigger current to go into the collector and leave through the emitter. Basically, it's as I said, it's a switch. So small current here, allowing a big current flow through. No current here, gets switched off, nothing goes across. So that's pretty straightforward as well. Okay. With that knowledge in our heads, let's have a look at how diodes and transistors can be combined to achieve the logic relationships described here. So there are two broad categories: diode gates and the transistor gates. So diode gates primarily consist of diodes, and transistor gates partially achieve their functionality through a combination of diodes and transistors. So let's look at some simple ones, simple diode gates first. So let's look at here. So we have two inputs, A and B, each connect to a diode, leading to an output. So what does it do? Let's consider. If we apply no voltage on either terminals, then there will be nothing out, wouldn't it? So we actually end up with 0, 0. So two inputs, 0, and then no output. Now, if we apply a voltage on either one of them, if we apply here, then, well, the current will go straight through to the output, give us 1, wouldn't it? So if A is on and B is off, the output is 1. Similarly, if we apply a current into B, but leave A off, we have 0, 1, and there still be current going through the system, and going out will give us 1. And of course, if we apply a current to both of them, everything will go out and leading to a high in the output as well. So that's essentially the relationship defined by OR, isn't it? Either A or B on will leading to the output being on. Okay, so that's pretty straightforward. Let's look at something slightly more complicated. Okay, big difference, as you can see. These are not grounded, but there is an active voltage source. So what does this actually do? Well, let's imagine what if we have both of them off. If both A and B are off, then the diode will act as a restrictor to the flow. So the current will only flow this way, and then there's good chance that, well, it's not good chance. The current will flow through these, and not much will be going out, leaving a low in the output. If either A is on or B is on, so let's say if A is off and B is on, the current, what happens here is if B is on, there will be a voltage here. What it does is it creates forward bias at this diode, which means the current can no longer flow through here. But all the current can still flow through A. So still leaving not enough to exit through the output, and we get a low as well. Similarly, if we switch A on and B off, it's exactly the same process. A on, B off, the current will just straight go through a B. Still not enough to activate the output, so we still get a 0 output. However, if both of them are on, if both diodes have a voltage on this side, it means that voltage coming out from the voltage source can no longer pass through either of them. Then all the current will have no choice but to exit through the output. So if both of the inputs are on, then the output will have to be on as well, because both of them are forward biased. No current can go through either of them. They all exit, and you end up with on. So that's the relationship defined by an AND gate, isn't it? Because both inputs have to be on for the output to be on. Okay. So these are the diode gates. Now let's look at transistor gates, basically gates that have transistors in them. Well, let's look at this one. Let's consider what it does. So we have 2 resistors here and a transistor here. So what happens if we apply, well, as you can see here, we have one input. So what happens if we apply a logic low here? Well, if we get no voltage here, then there will be no current going into the base of the transistor. So there's nothing here, which means the transistor won't switch on. So all the current here will be going out. So if A is 0, transistor stays off, all the current will go to the output, which gives us 1. Now, if we apply a voltage here, there will be current going into the transistor, which switches on, and all the current will pass through, going into the collector, exit through the emitter, and going to the ground, leaving not enough voltage to the output. So if we have 1 as the input, then the output will be 0. Yeah, that's basically the function of a not gate, isn't it? Inverter, because low here, switch off, all the current goes out, gives us a output high. If we apply a voltage here, current goes in, switches on the transistor, current flows into the ground, giving us a logic low. So that's a NOT gate. That's fairly straightforward. Now let's have a look at another one. So as you can see here, this is more complicated, has more moving parts. 2 inputs, each connect to a diode, and then they all connect to a transistor. How does this work? Now let's trace out the logic relationship here. So firstly, if we have a low on both inputs, so let's say 0 and 0, what happens? Well, you can see the voltage source here. The current will go from left and right as with a parallel circuit. The current on the left-hand side, because both A and B are low, so they can just, the current can just go through the diodes, yeah, and exit through the input terminals, which means there will be nothing or not much coming across here to activate the transistor. So the transistor will be off, which means all the current that goes across on the right-hand side will not be able to go into the ground via the transistor, and will have to leave here. That's giving us a logic high. Okay? So this is pretty straightforward. Now, what if we have one of them, say, A off and B on? So 0, 1. Okay, it's more or less exactly the same as the previous case. So the current will just leave through A, even though B is blocked here. But all the current on the left-hand side can still leave through A. While the right-hand side, because there's still not enough current to switch on the transistor, the current will just go out and give us a high output as well. So exactly the same thing if we reverse the relationship. Yep. If A is on and B is off, then all the current on the left-hand side will leave through B, and the current on the right-hand side will not be able to go into transistor and will leave and give us an output high. Things only change when we switch both inputs on. So high here, which means both diodes will be forward biased, so no current can go through either of them. That means all the current coming out on the left-hand side will have to go into the transistor, going to the base, which switches the transistor on. So once the transistor is on, that means all the current on the right-hand side, instead of going outwards, will go through the transistor and directly into the ground, which gives us a output of low. Okay, so which logic gates achieve this relationship? Of course, it's the NAND, because only if A and B are on do you get a like off in the output. Otherwise, it will always be on. So in an AND gate, this will give you 0, it gets reverting to 1. AND gate, this gives you 0, it gets inverted into 1. In AND gate, this gives you 1, gets inverted to 0. So this is the structure of a NAND gate. Now, and lastly, let's look at the of course, you can probably guess by now this will have to be the last one, which is NOR gate. But it's still good to have a look at how the operation side of things is. Right. So we have a voltage source here, we have ground here. We have 2 input terminals, each connect to a transistor. So what happens if both A and B are low? Both A and B are low, so neither of these transistors will be on, so all the voltage will flow through and leave and goes out. Yeah? But what if we turn one of them on? So let's say if B is on and the A is off. So that means A is off, so this transistor will still be off, but when we turn on B, the current will go through here, turn on this transistor, which means the current from the voltage source will go straight into the ground. And that gives us nothing to go into the output. So that will be a output low. Now, similarly, if we turn on A and switch off B, it's exactly the same thing. So if a current is applied in A, this transistor turns on, so the current from the voltage source will just go straight into the ground. Once again, nothing will leave out. And similarly, here, when we have both input terminals on, that means both transistors will be on, and of course the voltage will just go straight into the ground and still gives us 0. So this is the basic structures of logic gates, and so there is that.